Great. Well, I'll get into it. So thanks so much for the opportunity. Sorry I couldn't be there in person. I was hoping to attend, but I've got to be in the area in like a few weeks, and I couldn't make two trips. So today, so I'm Josh Mutus. I'm the director of quantum materials at Rigetti. I do a lot of the sort of pathfinding research for what ends up in our systems in the next like 2 to 5 years. So I'm going to talk a little bit about how our systems work and what the like long-term outlook is for not so much outlook, but looking at what systems of tomorrow might look like. So if we start making something that can rival or complement HPC at that scale, at that utility scale, what would a system based on superconducting qubits look like? So I want to answer two questions today. I only have about 30 minutes, so I'm just going to kind of pick my battles. I want to give everybody an impression about how we build quantum computers using a particular platform that I'm familiar with, superconducting qubits. So how we actually make the hardware, how it looks, give you a feel for all of that. And then I'm going to talk about if we look far into the future for when we have we're confident that quantum computers can solve problems that are intractable on classical HPC, what might such a utility scale quantum computer look like? Based on the hardware that I'm talking about early in the talk. So just to acknowledge, all this work is done in like collaboration with hundreds of people internally and externally from Rigetti. The fault tolerance stuff I'm going to talk about at the end is part of the DARPA quantum benchmarking program, and so I have to put this attribution at the bottom. So I'm going to talk a little bit about Rigetti Computing itself. So we're a full stack quantum computing systems company based in California. We have two facilities, one in Berkeley, one in Fremont. The one in Berkeley is where all of our hardware design is. Most of our fridges are installed, where we do most of the hardware and R&D and characterization of the systems. In Fremont, we have the so-called Fab 1. So we have a dedicated clean room dedicated to fabricating superconducting qubits and developing and packaging and developing new technology based on that. And this is kind of unique among superconducting startups for sure. But it affords us a really good opportunity to be able to do things at the entire stack of the hardware. And we also have a subsidiary in the UK. It was based in Oxford, it's moving to NQCC. We have a Rigetti UK. I'm going to talk from requirements out, so the design goals for quantum computing out about to motivate how these quantum computers work. So it's your quantum week, so I'm sure you've been hearing about quantum computing in general. There's a few things that you need to be able to do with a quantum computer in order to actually use it. You have to be able to create some addressable quantum state. So like a logical states that you can then do computation with. We use the ground state, first excited state of a resonator. So you have to be able to control that qubit state with arbitrary manipulation. So be able to set 0 or 1 or some superposition therein. You have to make that system insensitive to noise, so you can actually execute some kind of algorithm or benchmark with sufficient fidelity. And most importantly, you have to be able to entangle two qubits. So starting from these design goals, I'm going to talk about how we create hardware that addresses these. The first is, how do we get these states that we're talking about? And one of the things I really like about superconducting qubits in particular is it sits at the junction between quantum mechanics and very conventional, very basic, like undergraduate electric circuits. So you can think about these systems quite completely in both ways. So you can think of a Hamiltonian if you're sort of a quantum theory physics person, or you can think about an electrical circuit if you're more from the engineering side. And so the way we start is I like to think about it just a very simple LC oscillator. So this is something that I'm sure many of you in the audience are familiar with if you've taken undergraduate electric circuits. This is an inductor and a capacitor in parallel. And if you supply some energy to this, say at its resonant frequency, energy will resonate between charging this capacitor and then discharging to put current through this inductor. And if you were to somehow have no resistance in the circuit, energy would oscillate back and forth between this inductor and capacitor. And if I were to plot the states of this energy, you'd get this ladder of equal spaced energy, excitation. So if I put one excitation, going from 0 excitations to 1 excitation, it'll oscillate at that frequency. If I add another photon to it, it'll be exactly that frequency to go to 2 photons and then get another excitation. And if it's like I said, cool, if I get rid of all the dissipation, this can behave quantum mechanically because I can manipulate an individual photon and excitation in the circuit. However, I can't address it because if I'm using a control signal to apply energy to it, I can't decide, or I can't control whether I'm going from the 2 excitation state to the 3 excitation state, or the 1 excitation state to the 2 excitation state, the 3 excitation state to the 4 excitation state. It's not an addressable state. What we can do in a superconducting qubit is we have this special fourth circuit component. So everybody's familiar with the 3 circuit components: inductors, capacitors, and resistors. Everything's basically made out of those in sort of like passive microwave circuits. However, there's this fourth component that superconductivity allows you, which is called a Joshi injunction. And that's essentially a nonlinear inductor. So just like an inductor, the amount of current, when you apply a current through it, it changes the voltage. But in a Joshi injunction, it happens nonlinearly. So you can think of it taking this like very traditional harmonic oscillator potential and just widening it slightly. And the effect that has is to separate these levels out just a little bit, so that if I excite it with a microwave pulse, going from the 0 at this frequency F01, it'll just take me from the 0 state to the 1 state. And if I apply that again, it'll go back the other way, 1 state to the 0 state. It's not going to start carrying me up in this ladder. So in that way, I can address specifically this 0 and 1 in the qubit subspace. Now, how do I decide or design what frequency I actually want to use to excite my qubit? And this is kind of a thing that I kind of find kind of neat, because the physical parameters that you can access with your hardware really dictates this. The lower bound in these is about 3 gigahertz. And this is basically set by the lowest temperature we can controllably get to. So like I said, we have these energy levels. We want to make sure that they're not being populated by just black body radiation. Just any energy that's around in your system. You don't want that to be kicking your qubit state from the ground state to the 1 state. So we want to go to a frequency. We want to get to a temperature as cold as we can without spending a lot of money. And we want to create a frequency, or use a frequency that is comfortably above that. So it's easy actually to get, I can buy, like, from several commercial vendors, a dilution refrigerator, which gets me down to 15 millikelvin. A 3 gigahertz excitation, 3 gigahertz photon is 150 millikelvin. So that sets my energy, my frequency to being like 1/10 of the actual energy available. So that means that any transitions in that are going to be really suppressed by the black body radiation. And the upper bound is kind of more of a practical one. It's around 10 gigahertz. And it's basically what can we buy from commercial telecom for arbitrary waveform generators, DNAs, the cables that we use, and sort of cheaply enough, everything because of the revolution in 5G and all of the cellular telecom, there's just a lot of hardware that we could take from to actually build this hardware. And so that sets us essentially in this 4 gigahertz regime for our qubits. And the next thing is to have insensitivity to noise. So this is where the physics kind of come in. If I take this harmonic oscillator that I was talking about, the electric circuit, and I plot out its Hamiltonian. So I track its energy, and I'm not going to derive it, but you can just sort of like take my word for it. You get these two terms in here. You get the charging energy, so the energy that you get for charging the capacitor, and the Josephson energy for storing your energy in a Josephson junction. And if you plot those versus the number of basically electrons in your circuit for some parameters, so if the ratio of these two energies is the same, or is 1, so they're around the same energy, it takes just as much energy to put another electron on this capacitor as it is to flow through the Josephson junction. You'll see that the frequency of this oscillator changes very drastically. So going from like 15 gigahertz down to 8 gigahertz, if you take half of an electron off of it. And that's too much noise. If you have any noise in your terminals, it's going to create frequency noise in your qubit. It's going to change those transition frequencies that you care about. It's going to make it impossible to operate. However, if you set this ratio to be really high, that is, you have your Josephson energy to be like 50 times your charging energy, these bands flatten out. And this is what's called the so-called transmon regime in the jargon of the field. So if somebody mentions a transmon qubit, they're setting this ratio itself. And what this does is it gives us a resilience to the noise in our electronics or things around that. So it allows us to operate our qubit more easily. It gives us much longer coherence times. And this was really the revolution in superconducting qubits. The thing that took an interesting oddity, this Cooper pair box quantum qubits, into something that you could actually make performant. And so I'm talking about this not necessarily because it's just interesting physics, but like I mentioned, it's at the intersection of this electrical engineering is I can now take these ratios, this EJ to EC ratio, combined with the frequency that I can get access easily experimentally or commercially, and I can actually deduce the circuit parameters that I would get for these superconducting qubits. And so you get these kind of like what I call canonical like transmon parameters. So any superconducting qubit company that's using transmon qubits, so like us, like IBM, Google, probably others or academic groups, they're using sort of around these parameters, plus or minus, say, like 50%. And so I can go from the physics, the Hamiltonian, an analysis of the noise, the temperature regimes that are accessible, and I can get a capacitance. So I can know if I want to put a piece of metal on a wafer, or two pieces of metal to define a parallel plate capacitor, this is about the capacitance I need. This is about the inductance of the Josephson junction. And I always find that kind of neat. And so then I can take those parameters and I can design something. So I can put metal on a wafer and define my Josephson junction and make something that operates like a qubit. And so I'll walk through this a little bit. So this is how some of our like early test qubits looked at several different length scales. So starting from, and these are all different kinds of electron microscope images. This is a scanning electron microscope image. It's actually quite large. So this is like a 200 micron scale bar. You could take a similar image to this with an optical microscope. You can see these structures by eye. And if you have like just a good camera with a telephoto lens, you can actually like take pictures of them like when they're warm and not packaged yet. These big pads, so define our capacitor. So these are everything that's kind of light gray is a metal. It's an niobium in this case. Everything that's dark gray is the underlying silicon substrate that's been revealed through a chemical etch. So everything you see that's light gray is metal. That 100 femtofarads I was talking about is the capacitance of these electrodes between each other and between ground, and that defines this charging energy. You see this tiny little sliver of wire connecting here, and that's that inductor I was talking about, special inductor called the Josephson junction. So you zoom in, you see if you're at this higher magnification, you can see there's kind of a cross. And what this cross is it's a crossbar of two electrodes that are defined during the same process, but that enclose a very small barrier of aluminum oxide. So if I now take a cross section along here, flip it on its side, what this looks like is I have an aluminum electrode, and then I grow a very thin film of aluminum oxide, and then I put another electrode on top of it. And this is what the Joshi junction is. This here is kind of the magic part of the superconducting qubit. This is what defines our nonlinear inductor. This is kind of the most important part of our system. And if you zoom in even more, you see it's like around a nanometer. So the performance of this qubit is remarkably dependent on the character of this like 1.3 nanometer aluminum oxide film. And here I'm just kind of rephrasing the things I talked about before. We're at 20 millikelvin. And so these are all superconducting metals. That's a really important part of it because we don't want that dissipation. But that superconductivity gives us that macroscopic quantum state that gives us essentially the Josephson relation. So if you have a superconductor with a barrier in between, that phase drop of the superconductor tunneling across the barrier gives us that nonlinear inductance. So we can define more than just an individual qubit on a chip. This is an early test chip that we have that is, it kind of looks like hieroglyphs or some kind of like drawing from an ancient civilization, but it's actually a superconducting qubit chip. And it's illustrative because it shows all of the different components that we need to make a superconducting qubit device. And again, this is sort of universal across all of the various efforts in superconducting qubits. Everybody will have sort of the same components, maybe shaped in a different direction, but you'll have basically the same things. So you have the qubits themselves, which are these big pads where the capacitance defines the operating frequency of the qubit. And the junctions are too small to see on here because this is like a 5mm chip. Those are themselves capacitively coupled to another resonator. We call that the readout resonator, because in order to measure the qubit itself, you don't measure, you can't just apply energy to the qubit without decohering it. So you measure the state of a resonator and infer the state of the qubit. We have drive lines that are very weakly coupled so that we can apply energy to tune the qubit or to excite it into and control its state. And then we have couplers between the qubits that we can now control to execute 2-qubit gates to manipulate and interact the qubits with each other. And so here's a whole bunch of Hamiltonians, which you don't have to know, but it's just sort of important to show that they exist and that we can engineer them. And basically, I can show that the context of like how this chip fits into the larger apparatus and what we do at Rigetti. So this chip itself, it gets packaged up into a pretty like normal printed circuit board, pretty conventional printed circuit board. And these can either be perimeter wire bonded to this printed circuit board, where it breaks out to a series of microwave connectors. We have newer generations where this is addressed through substrate vias, and we put we squish the chip onto some sort of like compliant joint interface, and all the signals go through those vias. That puck, this PCB and mechanical connections defines the so-called puck, which goes at the bottom of a cold finger, excuse me, and all the connectors attached to the microwave connectors attached to this printed circuit board. This printed circuit board, this whole puck and connector setup is surrounded by a magnetic shield and infrared shielding to kind of protect it from its environment. And then the cables themselves go through a series of signal conditioning, like passive microwave components. So circulators and isolators for the readout, various filters and attenuators for all the microwave lines. And this goes at the bottom end of a commercial dilution refrigerator, in this case, a Blue Force One. And so the dilution refrigerator is the piece of hardware that we use to get to this like 15 millikelvin temperature. And you'll see these various layers of metal. The way that a dilution refrigerator is engineered is it's kind of like a set of nesting dolls, where each inner lower temperature shield stage is shielded by a slightly warmer exterior shield. And so this plate defines the 10 to 15 millikelvin stage. And we put like a copper shield around that. And then there's another plate here that's 100 millikelvin, and we put a copper shield around that. And that means that this inner very, very, very cold stage, the lowest temperature stage, is only seeing infrared from the 100 millikelvin stage. If we didn't have these cans, then just the infrared radiation from room temperature blasting the shield would keep us from getting cold. And so this process happens all the way up, again, at 800 millikelvin, at 4 Kelvin, and at 50 Kelvin, so that we can insulate and cool the whole thing. There's a vacuum can that goes around that. We pump the whole thing out. It gets to really low pressures and really low temperatures. And all the way up, we have a series of kind of like either custom or commercial hardware that we use for operating these systems. We can get really high fidelity two-qubit gates. So this is recent results that one of my colleagues, Shin Wu, shared at March meeting. We can get 2-qubit gates now kind of comfortably above 99%. A detail which I'm including on the slide, again, to sort of show the electrical engineering meeting the physics here, is that this performance is really depends on our ability to do precision pulse shaping. And so what we can do is optimize and engineer this pulse. So this is a screen grab of what our like arbitrary waveform generators are sending to this qubit. And by doing that and refining it, we can get this really high performance. And you can see all of these like different rise times and ringing and stuff. This all has to do with the particular of the signal distortion present in the cables and all of the very like the details of what's going on in the system, the frequency of the qubits, all of that. But the take home message here is that we can actually like take all of this and we can engineer really high fidelity systems. And one of the things that we're really proud of at Rigetti is our ability to kind of, our investment in these scalable technologies. So not only can we create a 2-qubit gate on a single chip, we can create a 2-qubit gate that spans 2 different chips. So the thing that unlocks these really high fidelity 2-qubit gates and superconducting qubits are these things called these tunable couplers, this component that bridges 2 qubits. And we can bridge those across 2 different chips and then get a fidelity, again, comfortably above 99%. This is the kind of technology that I think is going to allow superconducting qubits to scale really favorably compared to other architectures. And I'm going to talk about that a little bit now. So how far can we take this technology? I've got about, I think, like 10 minutes left. I'm going to talk a little bit about the sort of like distant future, almost the science fiction side of things. And this is the stuff we've been doing for quantum benchmarking. Today, we're at these relatively low fidelity systems with relatively small numbers of qubits. So say like 100 or so. Our largest system is 84 qubit. And what we know from the literature is that solving big condensed matter systems or ground states of molecules to, like, say, help a pharmaceutical drug discovery or a biologically relevant problem, you're going to have to get to really, really, really low error rates, so high fidelities, and like large numbers of qubits. And what could a system like that actually look like? So any system that we think now will have performance to do one of these utility scale architectures is going to depend on quantum error correction, we believe. So to do any of those algorithms, we're going to need fidelity in the like 10 to the minus, or 10 to the minus, yeah, error rates in the 10 to the minus 15, 10 to the minus 20, 10 to the minus 25 rate, which are just really small. And we think intractably small to make the actual, we don't think we can make individual qubits good enough to do that. So what we want to do is take a lesson from digital electronics and from telecommunications and encode our signals in some way that we can correct for errors and be resilient to errors, but still get the fidelity that we want with some overheads in time and space. And the way we do this is we do something called quantum error correction. So each one of these dots in this cartoon here, each one of these dots, these black circles and these white circles, are individual physical qubits, kind of like the ones I was showing before. They're all connected to each other by these yellow or green blobs. So these yellow or green blobs just say interaction, or pretend there's just wires connecting these. So we have a square lattice of superconducting qubits. They're all doing some repeated algorithm. And the take-home message here is that you can take a patch composed of these individual physical qubits, run some algorithm on them repeatedly, and this block will behave like a composite qubit that performs exponentially better than the individual qubits itself. So you get an exponential suppression of errors that scales with basically the number of qubits that are inside one of these blocks, which is known as the code distance. So here you have the physical error rate and the logical error rate. So the error rate of any one of these individual qubits and the error rate of the block, the logical composite qubit as a whole. And so at distance 3, you get some sort of suppression here. But as you keep adding qubits, you get this really rapid suppression of error. And this is sort of the goal of the field right now, is to start doing demonstrations and prove that this actually works. Now, going back to the electrical engineering, how would I make a lattice of qubits based on this code? And what are the limits that are imposed by like the physical hardware? And what might this system kind of look? So I can take this cartoon from the Fowler paper that's here and just map this onto our hardware. So we know for high fidelity, we need a qubit and we need a coupler. For the engineering, I know that I need at least one line for the qubit and a ground return, and one line for the coupler and a ground return. And I can just work out the geometry, and I can see that the qubit pitch that I get, so the pitch from qubit to qubit, is essentially 4 times the signal, or this interposer pitch. And so commercially, so if I can buy or make or design an interposer that's 250 microns pitch, I can get a 1 millimeter qubit pitch. Using this kind of like couplers to span, to join qubits on neighboring chips, we can start to design an architecture where we put all of the complicated, sort of low yield, expensive processes onto individual qubit chips and mount them onto a large carrier that has like fewer features. It's just easier to build, something that we might be able to get like a flat panel display manufacturer to make us. And the only thing on that are like essentially these couplers that tile between things, the things I talked about a few slides ago that we've actually proven out in the lab. But we don't have to make like incredibly large qubit chips. We can put all the complexity into smaller chips and then tile them. If we take this approach and we do the math, we start to see like we can actually fit really large numbers of qubits in like the size of things that we deal with every day, and then you see microfabricated devices with every day. So like a 1.6 million qubit fridge fits like mechanically in the largest fridge that you could buy commercially. This is this Key-Day fridge from Blue Force, and we actually have one of these. And what it looks like is, it basically looks like if you took a 55-inch TV and you bolted it to the bottom of that thing. And so superconducting qubits sometimes gets a bit of skepticism because the qubits are so like macroscopic. Like I said before, you can see them with your eye, you can take nice pictures of them with the camera. But because they're small enough, you can get really large numbers of qubits into a really small area. And the limiting factor isn't the qubits themselves, it's actually the density of the interconnect. Now that's only part of the story. We actually have to be able to cool all this stuff down and do some and address it with signals. So we've done thermal modeling to see kind of like, will this fit into large systems, and where is the bottlenecks in terms of thermal performance, and we see that's kind of okay. There's more engineering necessary. We can't fit 1 million qubits in, say, one of these fridges. We'd probably need to tile like 10 of them. So it gets us this 3 by 5 meter thing. And then at this scale, we'd need we'd have to go from individual cryocoolers that we use every day to something that's more conventional in the particle accelerator community, where they use to cool these giant cryostats, which are these particle accelerators, or the detectors therein. You need to use cryoplants. And so if we borrowed one of those from our collaborators at a Fermilab, we'd end up with a footprint like this. So if you took the total footprint of everything that we're doing the accounting for a 1,000,000 qubit quantum computer, we'd end up something that's pretty big, but it's actually not that big. It's smaller than a Costco. We build big things every day. If we have like an actual truly useful application for us, this is something that we could do the engineering for, that we could really start pushing on to build. But then we start to get into manufacturability and targeting and all of the like the hardcore engineering. And this is something to highlight that we developed recently, is the ability to like really precisely target our qubit frequencies using a conventional probe station and a pulsing scheme that we developed in our lab. I forgot to put the archive link, but it's, if you look up alternating bias assisted anneal, we can take our Josephson junctions, that really important part I talked about before. We get an as fabricated kind of spread, and by applying this pulsing scheme, this treatment scheme that we developed in our lab, discovered and developed in our lab, we can drastically narrow those distributions. So there's a lot of work that we're doing on the manufacturability here. We can tie all this together and we can create an architectural model and do the bookkeeping for how long and how much energy it'll take to actually execute like a large scale algorithm. And we can do that. So this is the work that's been primarily driven by this DARPA program, is we take like large, like expensive applications, like condensed matter ones, like Fermi Hubbard model or transverse Ising model, and we see how these scale in terms of runtime in seconds, and the number of physical qubits, and see like if I wanted to do a like 10 by 10 Fermi Hubbard, which is a pretty hard calculation to do time evolution dynamics, 10 by 10 Fermi Hubbard, like how long would this take on this proposed quantum computer, to how many physical qubits, like how much of a cost scale are we taking up? We can look at trade-offs. We can figure out how much time is being spent. There's some details here that I'm not going to get into. Just the tools exist. We're writing a paper. We'll be open sourcing these. I think it's just interesting to share. And we can see like how sensitive these are to various parameters in there. But just to end, just wanted to leave people with the impression that we are making noisy quantum computers out of superconducting qubits every day, superconducting qubits every day. We're pretty sure quantum computers will be useful, but they'll probably have to be really big to really overcome these orders of magnitude head start that classical computers have. We're studying applications to bring down these overheads, and we're developing devices every day to make them better. And I'm always happy to talk more. So thanks for the time. Thanks for the opportunity. I'm happy to answer any questions. But yeah, thank you.
Thank you, Dr. Mutus. I think it's time for some questions. Can you hear us?
Yeah, I can hear you. Yep. Okay. I can't hear any questions from the audience. I could probably only hear you.
What about you just come over here and talk to the computer?
Thank you.
So when you are doing the simulation like IC models and stuff like that, do you worry about the accuracy as well, or just the performance as time goes by? What is the motivation for that?
Yeah. So the accuracy is in creating the circuits for these resource estimates. The accuracy and the success rate are the biggest driver of like how big these circuits end up being. So if you want to do it so that it's not within any precision, you can get really, really low numbers that aren't very useful. So hidden behind all this is working with a bunch of subject matter experts that say like, we need to use the Fermi Hubbard model with these parameters and with this precision, and kind of like nested in this other algorithm to like get a useful answer out of it. So I don't know like the number off the top of my head about what these are, but that's kind of baked into.
So just a follow up, right? Let's say we are using Fermi Hubbard model, and how are the algorithm different for the qubit as compared to classical computations? Are they kind of different?
Yeah, yes. So here we're using like an algorithm called QSP, like based on QSP, like quantum signal processing, to do a time evolution of a Fermi-Hubbard model. Whereas in a classical computer, you'd be, I think the state of the art is doing like tensor network contraction or something like that. So it's a different algorithm that you'd be solving. But then there's a lot of like subtleties and like how you take the Hamiltonian and encode it in different ways. And there's, I don't know, talks and papers basically you could do and just trying to pull apart each of these kind of application instances.
Okay, just last follow-up question, like, so what is a scaling time as compared to the classical counterpart?
Yeah. So this is scaling polynomial, which is nice to see as you like. It's a straight line on this exponential, which is it's a polynomial scaling. So the nice thing about quantum is that they scale really favorably compared to classical, but classical HPC has such a head start in terms of this like 12 or 18 order of magnitude in terms of the number of transistors or bits of memory compared to the number of qubits you have. But yeah, they're scaling really well. It's just a matter of overcoming that prefactor to get to the system size where a quantum computer really overcomes the classical one.
Okay, thank you.
Thank you.
I wonder if you can estimate the number of physical qubits necessary to implement a single logical qubits, and how do you think this number is going to change over time?
Yeah, so that's a part of this calculation. So if you look at this table, we have that depends on the accuracy of the calculation you have to do, which tells you the accuracy of that logical qubit. So the error rate of that logical qubit. So say for this 8x8 Fermi-Hubbard, I know I need 265 logical qubits, which compile to 312,000 physical qubits. Not all of these qubits are used to create like individual logical qubits. Some of these are used for state distillation and some other and for ancilla. But part of this tells you exactly how many logical qubits you need per physical qubit based on some assumptions about the error channels in the physical qubits and so on. So the answer is it sort of depends on how long your algorithm is. How long do you need that logical qubit to live before you measure it or before the application is done? And so that's sort of a sliding scale. And so the goal of the field right now is to show that error scaling, to show that if I make a logical qubit out of 17 qubits, and then I make a logical qubit out of 49 qubits, that the 49 qubit one is like 10 times longer lived than the 17 qubit one. You want to see again this exponential suppression of error. And there's a lot of numerics that show this should work, but it hasn't really been robustly demonstrated in like a repeating error correcting code on actual hardware with really high degrees of error suppression yet. I don't know if that answers your question.
Is it fair to say that it's in the range of 1,000? No, basically.
Well, no, I mean, it depends. You can make logical qubits out of 17 qubits. So the smallest logical qubit that you can get error correction with is 17 qubits in the surface code. You could do it out of 49 qubits. It depends how long you want that qubit. So if you have an application that's really short and you just need it to be like 5 times longer than your physical qubits or something like that, then you could observe empirically error correction at 17 qubits. It's just the question is like, is that a useful logical qubit for any algorithm? At that point, it might be like 1,000 qubits. Yeah.
Thank you.
Yeah, thanks for the question.
Other questions? I have a last question, I guess, on the thermal side. I just wonder, it seems like this doesn't really consume too much energy on the operation, but on cooling sides may have some energy consumption. I mean, I don't know if it has a more impact if you stack more logical qubits together. So wondering how much heat it consumes, and is there any cooling challenge?
Yeah, I think if you do the budgeting for it, you can see that the largest consumption of power is your low noise amplifiers. So we have to read out the state of all of the qubits as some part of some application. And there we need a hemped microwave amplifier, and that sits at the 4K stage. And that's just a normal piece of electronics. It's the same principle as the like hemped amplifier in your cell phone or a base station or what have you. And but that consumes power to operate, and that creates a lot of heat load at our 4K. The next highest heat load is just like the taking normal metals and the thermal conductivity of normal metals, like leaking heat between the stages. And so all of this assumes that we can create some kind of superconducting signaling solution that goes between these lower stages, so the static loads drop tremendously. So if you have superconductors, in addition to having zero resistance, they also actually have really low thermal conductivity, which is a benefit, or it can be a real benefit in this case. So your thermal conductivity drops a great deal. So because of that, if we can engineer that, we think we have a path forward in these systems. But there's still like things we have to address, and that's where the modeling comes in.
Thank you. Any more questions? I have no questions. Thank you, Dr. Mutus, for talking to us, and I hope we can meet you in person sometime in the future.
Yeah, I love that. Thanks.